Hello guys, Earth here, and today I am showing off another system that I created based on Boolean Algebra. And, okay, well, it's a system for normal numbers using Boolean Algebra. So, what we have is we're using different conditions in products of these symbols. Let's take this I, for instance. We have, okay, let me change the color. We have xi times yi. In this case, it's the and I. I'll get to exactly what that means in a second, but we're basically just doing general conditions based on the signs, well, the signums of the x and the y. So let's start with the regular imaginary number first. So xi times yi equals negative xy. This just comes from I squared equals -1. That's not an issue. But let's organize this by the signum of the output. So I'll do absolute value of x, well, actually, no, negative absolute value of xy and positive. And this will just be else. And then xi times yi. And that's by do parentheses instead of just a dot. So as you can see, there is a clear XOR symbol there, and they're on the table. And what that means is that is the relationship between positives and negatives. So when both x and y are positives, xi times yi will be negative. And then when one of them is negative, and specifically only one, they're positive, and when they're both negative, then the output is also negative. Now, to you, this may be fairly obvious, but this is a table we're going to be changing, and I specifically is actually the XNOR case because of the not there. The table isn't really that obvious, but I is the XNOR case. So for XNOR, wait. So when you have 2 bits of information put with XNOR, so like, actually I'm not going to do X. I'm going to do A, XNOR B. I don't know what other symbol to use for this. So truth tables are fairly easy to make. Let's see. There we go. So when you have A XNOR B, that's supposed to be false. So when you have a truth table, let me write this. XNOR basically says if only one of the inputs is true, then the output will be true. So right now it would be false. So we have false, false, true, true. And now you can kind of see where this is going, and obviously XOR is the opposite relationship. So that'd be false, true, true, false. Now you can kind of see where I'm going with this. So back up here, the product of xi and yi is negative when, when x is less than 0 x nor y is less than 0, right? Let me see. Yes. X nor y is less than 0, and I should probably do that thing there. And regular multiplication, as in just x times y, would be x or multiplication. So let me actually make that smaller so I can erase the i's without erasing anything else. So x times y can be summarized using this in terms of the signs that it has. And now you can kind of see where we're going with this. I'll show you the first one, which I believe is the most useful, the OR J. So there you go, and there you go. And by the way, the diacritic there that I add onto the J is specifically for OR. And as you can see, this true and false part has both diacritics at the same time. Yeah, there's that. Okay. So for this, x or j times y or j is negative when x is negative or y is negative. I believe that's the or symbol. Could be wrong. And then obviously you can do the and j, which will be negative when x is negative and y is negative, and so on. So how does this affect multiplication, and how could it be useful? Hang on, let me. So the way it'll affect multiplication is actually kind of interesting. So for the OR J, we have the truth table. Signum table is what I'll call it instead. Oops, that's not what I meant to do. There we go. So when x is positive and y is positive, since neither of them are negative, you'll get a positive output. And for plus and minus, at least one of them is negative, so you get a negative here. And same for the other two conditions. So the way this affects multiplication, let's take this just the simplest forms of this. J to the n and negative j to the n. So, and we're only going to be quoting the signums of the outputs because it's just easier that way. So first, j to the n, since this is positive, and we're squaring it, meaning multiplying it by itself. Positive times a positive leaves a positive. So positive 1. And then multiplying that 1 by the OR j, we get positive OR j again. And a positive times another positive is again a positive, and that pattern goes on forever, and it's easy to prove. Actually, I'll write a few more j's down. So the next part of the pattern is what happens when the sign of the object is negative. Well, in this case, I'm going to do a j here. So negative j. And then when they're both negative, when the sign of the variable is negative that you're putting the power to, you'll get a negative 1. And then after that, you'll get, let's see, a -1 times a -j. Because this OR multiplication only occurs when you're multiplying two non-real units together and not when you're doing 1 times j. We're just doing regular multiplication. So it'll be a negative times a negative, and user arithmetic is a positive. So you'll get that. And then after that, a positive times a negative, well, positive j times a negative j. Since we're using this multiplication system, is a negative. So -1, and then this turns into a positive j, -1, because a positive times a negative. And then that pattern continues on. So in other words, x to the n, well, wait, no, I'm sorry. X or j to the n equals, let's see, oh, where am I? Okay. If x is greater than 0, wait. Yeah, if x is greater than 0 and n is even, we just get x to the n, yes. X to the n. And if n is odd, we get this, n odd. And if x is less than 0 and n is even, except for equaling 0, so n even and not equal to 0, then you just get, oh, where am I? Okay. Signum of x, that returns the negative back out, times absolute value of x to the n. I could have just replaced it with a negative, but actually I'm just going to show you right now. We can, since x is positive on this positive condition, we can actually go and write this as signum x, and soon we'll be able to compact it. And actually, we can just go ahead and do that now. And now we don't have to worry about that anymore. Well, other than n not equal to 0, but that's easy. That's a condition that everyone knows. If n's equal to 0, then anything to 0 is equal to 1. Well, anything finite. I'll get to that in a later video. But we've got that. Now we want to take care of these negatives. So if n is odd, x is less than 0, and n is greater than 1, we get, let's see, we just get x to the n j, right? Yes. And if x is, again, x is negative, n is odd. Wait, n is odd, so that'd be an absolute value. And we can also do the same thing here, an absolute value. Because x is greater than 0 anyways. And then, of course, we can then also combine this. So So we don't have to worry about this condition anymore. All that matters is n greater than 1. And there we go. And you can tell that we can compact this. It's obvious. And actually, let me just replace this, just to make it match. And then if n is equal to 1 or 0, so if n is equal to 1, then we just get xj, obviously. And if n's equal to 0, we obviously get 1. So what does this do? If we put this into a Taylor series, that is, listing all the powers out, as we saw up here, the even powers, well, when x is greater than 0, actually let me write this down, f of x or j equals, and then if x is greater than 0, actually, yeah, we won't need that. So if x is greater than 0, which I'll write all the way over here, we just get the even part of the function plus or j times the odd part. So the even part of the function plus or j times the odd part of the function. And let's see, is that, yes, that is correct. But if x is less than 0, if x is less than 0, again, we get the even part. Wait, am I sure? Actually, we did not get the even part in its raw form. We get 2f of 0, I think, minus the even part. Yeah. 2f of 0 minus the even part of the function. And you can verify that, because f of 0 just returns the coefficient of the 0th power of x, if we're considering Taylor series. And then if we're doing this, we get, let's see, the x term, so j, and then 2f prime 0, which returns the coefficient of the first power in the Taylor series, minus f odd of x, I believe. Oh, let's see. Minus f odd to f prime 0, let's see. Oh, well, I've got the x in the first place. Yeah, I've got the x there. All right, let me redo that. Minus f odd of x. Let's see if I did that correctly. That should... yeah, that should be correct. Well, except for the absolute value. There we go. And... yeah, I think that's it for that part. Actually, you know what? Let me prove this just by expanding this. So, if we do f of negative j, we get 2f of 0, which is the 0th coefficient, which we can't really expand. We'll just assume it's 1 for now. Minus the even part of x, so f of 0 is 1, and then the even part, I should do the absolute value. The even part is a 1, -1, -1, -1. That works, and then you have 2f prime 0 times x, so that is the first coefficient, times x, which, yes, that is true, minus f odd. So we get -2 or j because of this. Let's see, and then minus f odd x. If I do make a mistake, go ahead and leave it in a comment. I don't think I'll catch all my mistakes like I caught that one. Okay, so now that we've done the or j, let me go up. Let me do green, actually. Oh, oops. We've done the or j. Now, okay, and these are the regular ones, which I'm not going to cover because those are covered so many times. The I is the complex number where I squared equals -1. And the j is a split complex number where j squared equals 1. You can research those on their own. They have tons of applications. Now, as of right now, this or object just looks kinda out of place. But here's some applications for it. So let's say you want to take the square root of a negative number. I mean, obviously we could do this right with imaginary numbers. That's fine. But in this world, actually let's do just square roots of x. In this world, we don't actually get 2 branches for negative numbers. We only get 1. So let's say we're doing the square roots of -1. We will only get negative or j, and that's it. Nothing else. There is no second branch, none of that. And then if you do a positive number, so 1, not only would you get 1 and -1, but you'd also get positive or j. So the signum of the output of a root is the same as the signum of the input, always. And of course, you can do several other things with this, like later in the video, we'll cover cyclic versions of these. That is, when you square these, let's see. Yeah, when you square these, you just, I thought I was writing there. You just multiply by a constant again, like that. That doesn't look neat, but we'll get that type of constant later. So we've done that, and now let's do the NOR variant. So x NOR I, times y NOR I equals what? Equals, what was I going to say? Oh, right. Negative absolute value of xy and absolute value of xy. And then that is true. Well, the negative is true when x is less than 0, nor y is less than 0. And then you'll have elsewise here. And so that means the truth table, let's see. Truth table for this, when x is when x is positive and y is positive, this condition returns true. So we get a negative here and everything else becomes positive. So what does this do? Well, let's do a power sequence again. So negative, we're not doing j anymore, we're doing I. So negative I, no, I'm going to do I and negative I like that. So squaring I, we get, well, squaring the nor I, we get, let's see, -1. And then we get negative nor I. And since at least one of the inputs is negative, we'll get a positive output. And then, again, another positive. And then another negative. And this sequence will look slightly familiar, and, well, if you're experienced with complex numbers. And that's because this is the same sequence as complex numbers, so we can just show that a function of x nor I, if x is greater than 0, can be compared to what is it? To the function of xi. And then if we do the same type of thing, oh wait, that's the wrong sign. That's supposed to be greater than 0, I'm sorry. And then that's to a negative. So negative times a negative, because there's at least one negative in here, is a positive. And then that returns a negative again, which returns a positive. And that cycle goes on forever. So, in other words, this is comparable to f of xj when x is less than 0. Which is actually pretty interesting. When x is negative, you get a positive square, and when x is positive, you get a negative square. And this system, again, as you can tell, only has one root per object. Well, only gives one root to each object. So square root of 1 could either be 1, -1, or in this case, negative nor I. Then square root of -1 is only positive nor I. There you go. That looks not good. Let me redo that. So that's a pretty interesting application for that. And also, I think I should mention, if I do the original OR product, the original OR product on just real numbers instead of having i's. Let's do 2 OR product 3. Since these are both positive, the result will stay positive. But if one of them is negative, you'll obviously get a negative output. well, oops, that's the wrong number. But if they're both negative, again, you'll get a negative output, which is different from regular multiplication. But the huge application this has is is under this system, if you use this multiplication instead of regular multiplication, square roots, based on this multiplication, of an object are just the signum of the object times the square root of the absolute value of the object. In other words, square roots are completely closed. And really, any root or any power of any object other than, obviously, 0 to the 0. So yeah, that's pretty much it for the NOR multiplication. Let me go back up and mark the NOR done. Next, let's go over the ANDs. So the ANDs, by the way, I assume you could probably find some sort of inverse function formula for this, but I'm not going to do that right now. The AND system is, oh, oops, let me do a truth table. So plus, 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 minus, minus, plus, minus, minus. The AND system returns a negative only when all of the inputs are negative. So let's start with J and square it. So two positives are positive. Yeah, two positive JANDs are a positive 1, and this returns a positive. And that just goes on forever, which means that, again, the function of a positive input multiplied by J and will always be comparable to if you just use a split complex formula. So f of xj, of which is actually pretty interesting. But if you decide to go negative, let's do negative j like that. What you would get, let's see, is negative times a negative returns a negative, and do a positive. And then a negative times a positive, since they both have to be negative, in order to return a negative, will be a positive 1. Now, again, we can continue this system on. So negative, wrong J type is that. So, wait. Did I do that correctly? 1 times negative, that is negative that. Yes, I did. There we go. And then a negative times a negative, since they're both negative, will return a negative object. And then we get a positive j again. And then we get the positive 1 and so on. So again, this looks like an interesting pattern. And we can actually describe this as the real part of a function of xi minus the and j times the imaginary part. I think I'm using the correct symbols here. I'm not sure, though. It looks too much like a fancy L to me, but whatever. too late now, minus j times the imaginary part of f of xi. So again, we can represent imaginary numbers using the system. And so now we're going to do the nor and part. Or NAND, I'm sorry. We're going to do the NAND part now. So, plus plus, plus minus, minus plus, and minus minus. So the NAND system returns a negative only when both objects are not negative, or when at least one of the objects is positive. So we have that. So how will this look on a power sequence? Well, let's see. So we have the NAND system. Oh, that is the NOR I again, sorry. So we have x, no, we don't need x. We just need regular I and negative and I, like that. So two positives multiplied together make a negative in the system. So we get -1. And then a negative times a positive, and normal multiplication is a positive. So we just, oh wait, no, it's a negative. I'm sorry, it's a negative. And then in the new multiplication system, this times this, or negative times a positive, also returns a negative, so we get -1. And then that becomes negative and I again, and so on. And this specific system continues forever. So again, we get that 2f prime 0 minus, what is it? 2f prime 0 minus the odd part of the function, so f odd of x. Oh, I'm sorry, it's supposed to have an x there. That's for the imaginary part, and then for the real part, we can just symbolize that using f of normal I. Actually, wait, no, we can't. That'd be 2f of 0 minus f even of x. There we go. Now for the negative component, negative times negative is a positive, and 1 times anything is just that thing back, and negative times negative is a positive, and we get this back, and so on. So again, the odd part of the function, or the imaginary part, will just be 2. Wait, no, we don't need the 2 anymore for this. It'll be negative f of, well, yeah, negative f of absolute value of x. Yeah, that's correct. Negative f of absolute value of x. Well, the odd part, I'm sorry. The odd part will be negative f of absolute value of x, and then the even part will just be the even part. Or another way we can do this is it's the real part of the function of xj minus the and I, or NAND I should probably say, times the imaginary part of, actually I should probably do the m there, of f of xj, like that. And I should probably do an absolute value here and an absolute value here. There we go. And actually, negative j, 1, negative j, 1. Never mind, I can just do a regular old x. I don't even have to do absolute values here. So it's just xj and xj. You don't want to make the formula nastier than it has to be, right? Anyways, we have that. Now for the parts that I'm really excited about, which is the positive, well, all positive and all negative. So let's start with the j positive. So x j positive times y j positive equals absolute value of xy. And instead of going over the whole power sequence right now, I've done it several times. It's the same power sequence as split complex numbers. So you'll get the even part of the function at x plus all positive j times the odd part of the function at x. And if you want an explicit form for the even and odd forms, that's easy. The even form is just f of x plus f of negative x over 2. Then the odd form is just the opposite of that. So f of x minus f of negative x over 2. So that's all that means. Okay. And now, the all negative objects. So there we go. What should I call it? Falsi. Yeah, I'll call it falsi. X falsi times y falsi equals negative absolute value of xy. For this object, we get, let's do the power sequence again. I and negative I, like that. And again, so for the power sequence, no matter what we have, 2 of these i's multiplied together will always be negative. So negative times that will give us that. Oh wait, negative that, I'm sorry. And again, no matter what, we're just going to get a negative. So a negative times that again is that, and so on. And again, negative times negative is a positive. And no matter what, we're always going to get a negative, and so on and so forth. So now we get to write our function formula down. We get the odd part of the function at x, and that's all those being positive, so we want to negate that, which works for these parts and everything past these ones. But for this, we have to account for that. But we have to account for the first powers. So 2f prime 0 times x. That is a huge 2f. There we go. And then for the real part, again, that is also easy. You just get 2f of 0 minus the even part of x. And now, here's the application for this object that I've been using it for. If we apply this to the exponential function, we get f prime of 0 is just 1. So we get e to the x falsi equals 2 minus cosh of x plus falsi 2x minus sine x. And let me draw the graph real quick. All right, so that is the basic shape of the graph. I'm not going, actually no, I will go ahead and show you some values. So this 2x minus sine x, actually let me use a different color for this. I'm going to use the yellow. So the 2x minus sine x equals 0 at this point on the positive and negative sides. So log of negative 1, and actually, well, yeah, log of negative 1 in this system equals well, actually, log of some negative number, which is the output here, equals the all negative object times the all negative constant, which is around 2.177. And actually, that's plus minus. So equals, actually, I'm going to do approximately here. It's approximately plus minus 2.177 I. And I did use Wolfram Alpha to get more digits than just that. If I remember, I'll pop them up on screen right about now. But again, this is another symbol that I'll get to in a second. But that's interesting because it only allows for exactly 2 logarithms of this object. And well, obviously, if you want to, you could find an exact value for this. Like this would be logarithm of negative 1 should equal, let's see, logarithm of, I think it'd be 1 over cosh of that constant, which is the 2.177 minus 2, plus or minus that constant times that. The logarithm of an object in the system will always have at most 2 values, or 2 outputs. And if the real part of the input of the logarithm is positive, then there'll only be, well, positive or 0, then there'll only be 1 output. So let's do, for example, logarithm of 2 plus 3 that. So obviously it would be logarithm of some r plus the argument, which I'm just going to call theta or theta just to align itself with complex numbers more easily. So this, as you can tell, will only have one answer. So we have a positive and a positive. And the only part where both of these outputs, where both of the outputs from the exponential are positive is in this box right here. So as you can see, there's only one value for it. But if we wanted to do -2 plus 3i, let me change this real quick. What am I doing? There we go. There are two outputs for this function. So let's see, a negative real part and a positive imaginary. So that, okay. So that would be in this area about. There we go. So that's the first area, and then negative real and positive imaginary again. So, and then it would be out here. So, okay, you can't exactly predict one branch from the other, but as you'll see, it's pretty easy to see where the two different branches are. So that is a why can't I not write? Okay, that's a minus minus, and that's also a minus minus. The plus plus section is here. The minus plus, so negative real part and positive imaginary. Oh, wait. Oops. That's what that is. Okay, a negative real and a negative imaginary is in that part. So negative real, negative imaginary. And also in this part, so negative, negative. And then this last section is positive real, negative imaginary. So positive real, negative imaginary. From that, I'm sure you could come up with a good way to find the argument of this object. Well, you also have to find radius, but that doesn't really matter. So now that we have that, we've covered that application. Now I want to cover the cyclic objects. So I'm going to start with the cyclic J. Why can I not write? There we go. F of A plus B, cyclic J. That's a horrible tilde, but it's fine. It's supposed to look like that about. Anyways, F of A plus B, cyclic J. Cyclic J's rule is just cyclic J squared equals cyclic J, so it's regular multiplication. So instead of actually giving you the whole like power series and all that, I'm just going to give you what it would equal. So it'd be F of A plus cyclic J, F of A plus B, minus F of A. And you'll be able to tell that this kind of makes sense. The application that you would have for this is it's some sort of parallel one, which means that if you wanted to separate powers, well, separate something out of a power sequence, let's say A plus B to the n, and you want to separate the A out, this just does that for you. You separate the A out, and then you multiply B by cyclic J, and the A is just gone from there. Now, obviously, you could probably find some sort of inverse function, but I'm not going to do that. And then the other most useful one that I'm going to be using is cyclic I, whose square is its own negative. And again, instead of proving that, I'll just give you the function formula. So f of a plus b cyclic I equals f of a, I'm sorry. F of a plus cyclic I, f of a minus b. There we go. Now, there's one other cyclic object that I would like to show y'all that I have used and that I can see might have applications, and that is the OR J. So, cyclic OR J, again, we will do the multiplication table, so plus, 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 minus, minus, plus, minus, minus. And if at least one of the inputs is negative, the output will be negative, and then the positive there. So putting this in action, we'll multiply positive j by positive j, doing another series again. And let's see, positive j and positive j would be positive, and then that just goes on forever. But if we're doing a negative, which I don't know why I wrote a positive sign there, a negative times a negative, and this system is a negative. And then since it's a cyclic, we have negative cyclic j squared equals negative cyclic j. In fact, that works for any power of cyclic j. So we can just turn that into an n there. Well, unless n equals 0, but that doesn't really matter. So what this does, interestingly, is it separates the signum of the input of a function from the distance. So using this, we'll be able to see that we have f of x or cyclic j equals, when x is positive, you just get f of x. And when x is negative, you get, let's see, 2f of 0 minus f of absolute value x. Yes. Or in other words, we can then put an absolute value here, and that would be x is greater than 0. Yeah, and x is less than 0. And if we put this all together, we would get f of absolute value of x times signum x plus 2f of 0 if x is less than 0 and 0 otherwise. Now, if f of 0 is equal to 0, this part just completely goes away, and you're left with this. So this object automatically separates the signum of a variable, of an object or a number, from its distance. And now I could cover all the others. I could cover negative cyclic, I could cover cyclic nor cyclic and j, and a bunch of other things. And in fact, I'm going to go and cover and j right now, because and j does the same thing as or j when you put it into a function. So they can both be used for the same thing, but who knows, maybe you want some sort of benefit with or j that you don't get with and j. Now, of course, there's also the negatives, but, well, they're all negative cyclics, but I'm not going to go over those, mostly because I haven't found a good application for them yet. So I guess this is the end. So thank you for watching. Thanks for joining, and I'll see you in the next one. Bye.